There are two major types of flow when we think about both wind and water. One is laminar flow, and two is turbulent flow. Basically, the overall purpose of both of these movements is to be able to transfer energy from one place to another. In terms of the prototype wind tunnel that we have created, we will be dealing with laminar flow. Laminar flow is the flow in which the fluid travels smoothly or in regular paths, in contrast to turbulent flow. Laminar flow is sometimes also called streamline flow. Basically, this is where the pressure, the velocity, and other flow properties at certain points in the fluid remain constant. There are many modern applications of laminar flow. The first example of laminar flow can be seen in grocery cooling, where many food products are cooled in local supermarkets. These products are cooled so that their temperature allows them to be the best quality for consumers. Especially when the display cases are open, it is important to keep the chilled air at a limited amount of energy and temperature so that a lot of the energy is not wasted. Moreover, many grocery stores use laminar flow to control the energy that reaches these products so that in the end, energy is conserved. The second example can be seen in drainage systems in local communities where many of these communities had to use laminar flow to properly drain the water that flows through the streets daily after there is a rain shower. The communities use laminar flow especially because turbulent flow would require a lot more energy, and for drainage especially, only a minimum amount of energy is needed to drain all the water, and as a result, these communities turn to laminar flow to use this minimum energy to get the job done. Another common example can be seen by settling tanks that allow suspended particles to settle out of water or wastewater as these particles flow slowly through the tank, in the end providing purification. Turbulent flow would keep all of the particulate matter ingrained in the flow of the water. Furthermore, to solve this problem, by being able to use laminar flow, the particulate matter can easily drop out and flow out of the settling tanks. The fourth modern example of laminar flow can be shown through laminar flow cabinets. They create particle-free working environments by protecting air through a filtration system and exhausting it across a work surface in a fixed airstream. These cabinets provide a clean air environment for the various laboratories that exist throughout the world and many offices. Now, let's delve into the history of laminar flow. Before the 1950s, scientists knew about fluid flow as only one general topic, but this was before Osborne Reynolds' breakthrough in this field of laminar flow. Reynolds conducted an experiment which he presented in the Proceedings of the Royal Society of London that showed the distinction between laminar flow and turbulent regime. Reynolds' experiment examined the water flow in a large glass pipe, and then after visualizing the flow, he injected a small vein of dyed water into the flow and observed its behaviors at different flow rates. In this experiment, he demonstrated the existence of two different flow regimes, one called laminar flow and two called turbulent flow, which are both separated by a transition phase. The North American P-51 Mustang was the first aircraft that was designed to use laminar flow airfoils. However, a lot of research showed that the aircraft was not capable enough of maintaining a lot of laminar flow on the wing, so there had to be a much better solution. The use of airfoil on the Mustang would greatly add to the drag reducing concept. Because the Mustang wasn't capable enough to efficiently produce laminar flow, engineers at the North American Aviation NAA approached this problem with the plan to fill and paint the wing surface to provide smoothness to the wing to allow the air to move in a fixed pattern. The foil which was used for the Mustang had a thickness ratio of 15.1% at the wing root. The tip ratio was 11.4% at the 50% chord line. These numbers provided the maximum thickness area at 40% from the edge of the wing of the aircraft and resulted in a small negative pressure gradient over most of the wing surface. The consolidated B-24 Liberator came after the Mustang, and it also used laminar flow movement. Recently, the application of hybrid laminar flow to modern commercial transportation of the aircraft was successfully flight tested on the Boeing 757 aircraft. In the demonstration of the hybrid laminar flow, in which only the upper surface of the wind was designed for the attainment of laminar flow, a significant amount of drag reduction was measured in the wing.
Today we are presenting the laminar flow wind tunnel that we created this past couple of weeks. We first start off with the fan for the project. The fan is going to be pushing all the smoke through the experiment and getting it to that laminar flow that we're aspiring to get. Once we get through the fan, it's pushing the air toward the incense container, where it's going to have a burner box where we're able to light the incenses and get the smoke that we want. The fan pushes this smoke through this long horizontal tube that has all the filters to straighten out the eddies and all the turns in the smoke. Once it's straightened out, it goes to this vertical tube that also straightens out the wind just a little bit more, just so we can get that straight wind design that we want. To get this streamline, we essentially put 5 more straws just to straighten it out even more and as much as possible, just to make sure that we don't have a turbulent flow at the end. Once it runs out through the straws, as you can see, it's pretty clear that we have a very straight streamline, but eventually it does become disrupted just because of air conditioning in the external environment. The reason we couldn't close up this container was because it would have created a vacuum in a sense that would just contain all the smoke and wouldn't let us actually remove any of it, and so we would, after like 5 or 6 seconds, we wouldn't actually get to see the smoke. At the end of the day, what we got to see is that through our experiment, that even though smoke can start off as very turbulent, we can turn it into a laminar, more streamline, and then eventually it'll turn back into turbulence, depending if it were to hit an object or just be affected by external forces such as our air conditioner that pushed wind toward it.
Here's an example of how the laminar flow could be disrupted by an object to be able to cause this turbulent flow as a result. Wow, this example, throws an apple to disrupt the streamlined flow. Thank you guys so much for listening and watching this video, and I hope you learned a lot about laminar flow. Thank you. Bye.